All right, so whenever we're having reaction stoichiometry going on, we have to have a reaction. So you have to have a balanced chemical equation, BCE, before we can begin. The only thing that we need to, I just want to kind of quickly review is the type of reaction each of these are representing. So number one here, what kind of reaction is this of the 5 types of reactions? Decomposition, right? What is this? Ammonium dichromate, good. Okay, so if you had to balance it, you totally could, right? Go for it. You have this on your paper. You can write on your paper. Tell me what you get when you get it. Yep, it's just a 4. Because you see that your nitrogens, there are 2 nitrogens there, and there are 2 nitrogens there, and you see that you need 8 hydrogens, so the only fix is a 4 coefficient, and everything else actually is balanced. So we're good there. Next one, if I apply electricity to water, do you guys know what happens to it? It's called electrolysis. Right, so this is, again, is another decomposition reaction. And I'm writing the states of matter just to show you that you should be familiar with states of matter. Each of these are at their room temperature condition, but you don't always have to write the states of matter. So balancing it, do what?
Add 2 to H2 and H2O.
Okay, so here, and the oxygen is already balanced. So that's electrolysis of water. Next one, what kind of reaction is this?
Single replacement.
Lies.
Double replacement.
Double replacement. So an ionic compound and an ionic compound, they are just going to switch partners. What are the new products?
Calcium phosphate
And that looks like a 4. Here we go. And sodium chloride. Balanced. Can you tell me the coefficients across?
so you're added 3 to CaCO2.
Mm-hmm.
Added 2 to Na3CO4.
Uh-huh.
And add a 5 to NaCl.
6, right? Because you got 6 right there, 3 times 2. Of all of these, we should have one precipitate, okay? So which of them do you think is the precipitate in the product side? The phosphate, right? And I will quickly talk about my silly rule for how to memorize the general solubility rules. You do not have to memorize every single exception. It's good to know some of them. It's more in our next unit than this unit. But the things that are insoluble are chops. Okay? Carbonates generally are insoluble, excuse me. These are precipitates, okay? Hydroxides, oxides, phosphates, and sulfides. Chops, okay? Those are generally your insoluble ones. There are exceptions to each of these rules, but I'm not going to hit those just yet. Okay, and then what kind of reaction is the last one? Combustion, reaction with oxygen. What is this? Anybody remember that from organic? 3 carbons. Or prefixes, 3 carbons? No? No? Propanol?
On the way to your class, please allow us to your classroom. Thank you.
Okay, that is propane. So we've heard of methane, ethane, propane. Propane has 3 carbons: butane, pentane, hexane, and so forth. So combustion makes carbon dioxide and water, and balance. How do you start off? Yeah.
I was just going to ask for the nomenclature tomorrow. Do we have to know, like, propane?
No. We have an organic independent study. There are 4 videos of organic chemistry that you will watch on your own time in Unit 2. And that's what that packet is in your packet. It's got organic chemistry notes and it reviews that. I'm just seeing who remembers what right now. No, don't worry about that. Okay, so when you're balancing this, I always start with carbon. So I see 3 carbons. I need a 3 here. I see 8 hydrogens. I need a what here? On the water? 4. How many oxygens total over here on the product side? 10. So that's 6 plus 4 is 10. So I need a 5 right here. There we go. All right, so we can balance. We got this. But just FYI, when you are balancing, carbon come first, carbon will usually come first, hydrogen second, and then oxygen. It just makes it easier because oxygen appears in 2 different products, so it's easier to count it up last. Can I go forward? Okay, so whenever we're balancing, the only really goal is we need to have the coefficients so we can have a mole ratio so we can go farther to do our stoichiometry. So I'm going to do a couple of percent comps before we actually get into full stoichiometry, but because this is relevant for your lab for today. So percent composition is always based off a part over whole, just like a percentage in here. Last year, I had 12 girls in the class and 4 boys. Now it's flipped. I think we have like 13 boys and 6 girls. Okay, so the percentages have flipped, right? It's just part over whole. So if we're talking about a part over whole, you have to know the number of atoms, so you have to know the subscript, and then you have to know what the atomic mass is by looking at your periodic table. So potassium dichromate, formula. And we'll break it down. What's the formula of potassium dichromate? I'll start you off. Cr, so pro, 07, good, because dichromate is Cr, or Cr2O7, 2 minus. So the percent comp is basically the percent potassium, chromium, and oxygen. Let's just go through 2 and we'll backtrack to the other. So potassium's percent is 2 of the potassiums, because there's 2 subscript, times its atomic mass, 39.10 grams, if you look on your periodic table, over the total. So the total molar mass there, I thought I had written down. Oh, let's do geometry next year. I'm just gonna set it up for you guys. Okay, I'm just gonna put total. It's the total of everything here, and then the last bit is you're gonna multiply by 100. Do you remember this? Okay, this is very easy, but you should be able to do this for every element within the compound. So you take your subscript times its mass over the total molar mass of that substance. So for oxygen, what would you be doing? What would the math setup be? Oxygen. 7 times 6.00, right? Over total times 100. And if you wanted to get the last one without setting up the math, what would you do? Yeah, add these 2 and subtract from 100 because it's 100% is our total. So whatever these 2 percentages are, make up most of it, and the chromium will make up the rest. So that's our percent composition, and it's just percent composition is always based off mass. That's what I've taught you right now. Okay, it's always based off mass because that is generally what we are using in the lab. We're using the balances and we're massing things out, and then we also can evaporate water for something and see how much water leaves in terms of mass. So everything is usually based off mass when we're doing percent composition. Mole ratios, those are a whole nother story, so we'll get there in a second. Can I go forward? Okay. I know, first period of chemistry. So wake up for me, okay? For this one, I just want to go over the formula really, and then you tell me if I need any more. What's the formula of this? Pentahydrate. Right, so dot 5 waters, good. So a hydrate means that this is what you dealt with yesterday with the sodium thiosulfate pentahydrate. So you've got water molecules embedded in this crystalline structure, which gives it kind of a glossy appearance. You can dehydrate this to wipe out all the water. So this is called the hydrate. So what would the anhydrate be? Just straight up copper 2 sulfate, right. So this is a solid, and this is a solid. It's just this is a hydrated solid. And then whenever you are adding up your mole masses, and you saw this yesterday in your lab, you just add 5 times 18 grams per water. You do not actually multiply. I know that's a big mistake people make. So if I wanted to get the percent water in this compound, what would I do? Percent water. 5, 18, I got you, I just said 16 too. So 5 times the mass of water over total times, there we go. So hydrates, you just include the coefficient in front of the water as its subscript kind of thing. All right, reaction stoichiometry. Give me a smile every now and then, wink, something. Okay, so, oh gosh, one more thing. This is just a side note, we'll go over empirical and molecular formulas tomorrow or next day. So you know that whenever you're writing your ionic stuff, you always reduce down to the lowest subscripts because that is the empirical formula, and that shows the relative number of each atom in the compound. So we always want to make sure we are going to the lowest ratio. If we're going to molecular compounds like glucose here, if we're working with molecular compounds like glucose, we generally will stay in our molecular form. So we will get into that more later, but that's just a quick remember. Okay, so on this particular, I'm going to not talk about this just yet. Let's go into the problem, and then we'll backtrack if we need to, because I think you'll spark your memory. Whenever we're working with a word problem, the first thing you look for is what? Numbers that are given, right? So a given. You're also looking for the question. Please do your problems in a similar way. You're always going to want to identify the given. You're going to want to identify the question. And then if it's a reaction, you need to start off with a BCE, balanced chemical equation. It's kind of the first 3 things you really need to do before you can continue the problem. So when you're looking at this problem, what mass of potassium iodide? So stop. What do I know? But what else? I know the question. I know my question is, what's my grams mass of potassium iodide, which is Ki? That's the first thing I write because I don't want to forget my goal. If not, you're wasting your time. So what mass of potassium iodide is necessary to completely react with, what is this? Given 20.61 grams of lead to nitrate. And a double replacement reaction. So what else do I kind of know? I know the 2 reactants for this double replacement, and I just need to go ahead and fulfill it and write it out, right? So I'm going to write that kind of up here. You write this wherever you, I mean, if you fit on your notes page, you write it on a separate page. It's up to you. I like to at least print the problems for you, so you don't have to like write everything down. Okay, so reaction. Potassium iodide, because it says this is reacting with lead to nitrate. Okay, reaction. Products. Lead to iodide and potassium nitrate. Ooh.
Does it matter which way you started?
Does not. So I knew it was lead 2. The charge of lead stays the same, so that's why you do have to take that over with you. Balance it by putting a 2 in front of potassium nitrate and then potassium iodide. Okay, of these, what do you think? Which of these do you think is the precipitate? Lead. Okay, because we have heavy metals that are very commonly going to be precipitating out, and lead is one of them. Lead, mercury, and silver. Okay, so starting off with my given, what's the first step I must take to get to eventually to something else? Okay, so the molar mass, so 1 mole, and I do like for you to write out who in the world you were talking about. In this case, you're talking about lead 2 nitrate. 1 mole of lead 2 nitrate. I will give you the molar masses so you guys don't have to calculate. So I find my molar mass. 331.2 grams of lead 2 nitrate. Please write your identity. If not, I can't really check your work very well. So you'll see that grams of lead 2 nitrate, grams of lead 2 nitrate cancel. We need to get to Ki. What's our next step? Mole ratio. What is the mole ratio? Okay, so I'm putting what on top? So the Ki, so the 2 goes on top. So 2 moles of potassium iodide is reacting per 1 mole of lead 2 nitrate. Most people remember stoichiometry, so I'm going through this one quickly because you just are worried about canceling these 2 units here. So far, yay, 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 yay. I need to cancel out my moles of Ki now by getting where? Or using what? Molar mass of Ki, right. So, because my final, my question is grams of Ki, so I need to end with that on top. 1 mole of Ki weighs 166.01 grams of Ki. So 166.01. So, once you kind of go through, calculate 20.6 divided by 331.2 times 2 times 166. That's about half of that. And that cancels that out. So what's your answer, Bobby? About 20, right? You guys see that? You see that 166 and 331, that's about half, and then you have a 2 on top, so that's 2 over 2, which is 1, times 20.6. It's actually probably a little over, so the final answer, oh no, it's 20.66 grams. Okay, it's almost exactly. So you can actually go through the math quickly, looking at the numbers, give a quick estimate, calculate it, you can verify you have it right without worrying about, like, did I forget a parentheses or did I forget a decimal? Okay, use your brain. All right, quick review. You feel like you remember a lot? Some people won't shake their heads, some people will. Okay, we got to work on this. Okay, let's get through a limiting reagent one now. So, oh no, let me show you percent stuff. Sorry, I wanted to do this one too. This one's a little different because we're dealing with a solution that has a given percentage, which is 22.5%. 22.5% of something, okay? What is a percent again? So part over whole, right? So if you're writing this as a percent, you can't use it as a conversion factor. But percents are conversion factors if you write them as a part over whole, right? So this can be written as 22.5. What did I say percent pertain to? What unit of measure? Grams, okay? 22.5 grams of Ki, potassium iodide, in, so over whole, in this case percent is regarding 100 grams of Ki solution. So solution is mixed with what? Generally, aqueous solution. Water. So we have Ki in water. And of all that, there's only, if I had a full solution, 100 grams of the solution, and I, partitioned it out, I would only have 22.5 grams of Ki. So that is a conversion factor we will use. All right, so what mass of solutions? My question this one is grams of solution, of Ki solution. So in the end, what do I need on top? So grams of Ki solution. So I need this, like this, or flipped? Flipped. Okay, so just think about that. All right, so what mass of solution, that is 22.5% potassium iodide, is needed to completely precipitate, given 0.28 grams of lead to iodide. Okay, so far we know a conversion factor, we know our question, we know our given. What do we not know yet? BCE. So we've got to go back and figure out what reacted. What things do you know reacted? What's one reactant? Potassium iodide, right? Because it's saying potassium iodide solution is precipitating out this. So if potassium iodide is one reactant, what is a part of the other reactant? Lead. And I don't really care who it's bonded to, I'm just going to put lead 2. Okay, it's okay to write that. Because it doesn't matter who the anion is, it's not included, it's probably a spectator ion anyway. So this is going to do a single replacement. In this case, we're going to let it. So the K and the PB are going to change places to make lead 2 iodide and potassium ion. And truly, the potassium is a spectator ion as well, but I'm going to leave it like that as well. Okay, is that balanced? No. 2, 2. There we go. Okay, so then from here, we should be able to, pretty much go on like normal. So, taking my grams, go where? Okay, so 1 mole of PbI2 weighs 461.00 grams of lead to iodide. Next. What's next? So the mole ratio, yeah? You're going to Ki in some way or form. So we got to get rid of this. Sorry, we're going to go from here and here. 2 moles of Ki and 1 mole of PbI2, because you're comparing what we want to what we are currently at. Okay, so then here, we're kind of getting closer to our desired goal. What's our desired goal again? Solution, right? The whole solution. We're still stuck in pure Ki. Okay, so we need to get to something like this, because we already know we want this 100 or this grams of Ki solution on top. So I need to get to something I can cancel, which is going to be grams of pure Ki. So I need to take my moles to grams, specifically of pure Ki, which weighed again 166, I think. Yeah, 166.0 grams of pure Ki. Just give myself a little space here. Oh no. So far so good. And my last step is to take our grams of Ki pure and make them cancel, leaving on top the grams of solution. So I'm taking this percent that we previously saw and flipping it. So 100 grams of Ki solution is on top and 22.5 grams of Ki. So it's just a little different due to the fact that we have percents that we do have percents that can be used as conversion factors. So I don't know if we can do mental math really on this one part. Well, 100 times 0.28 is 28 times 2 is calculate that one. Point here. Final is 0.8962 grams of solution. So how many sig figs should I record to? 2. That's because this right here is a given. That's a measurement somebody took in the lab that has 2 sig figs. Why not 1?
You don't count more ratios.
Right, because a ratio is not a measurement. Sig figs are only limited by the measurement part of it because somebody's estimating it. Ratios are like a given, okay? So it's 0.90 grams because the 9 rounds up the 8 and then you leave a 0. Okay. Now we have like quick review of some vocabulary real fast, and then we're going to go through our limiting reagent. Everybody's favorite from honors chemistry. I told my honors kids I was basically reviewing with you in 2 weeks what they are going to learn almost the whole year. They're like, oh my gosh. Okay. So you do not have to write all of this down, huh?
I was just thinking it's not that bad.
It's like you remember. You do remember more than you think. So, this is me and my definition kind of thing. The highlighted or the golden one here, percent yield formula, is one that you absolutely need to know. I just want to do a quick review of like what the terminology means when you do this problem. You're like, oh, they say that they actually got this. You know you'd get theoretical yield. So you can write or take a picture, don't care, read, close your eyes and try to memorize whatever you need to do. But theoretical yield is literally theoretical. It's like, did I get something wrong?
No, I did.
I was like, son, you guys gotta catch me if I get something wrong. Theoretical yield is our la-la land product. Like if everything was perfect in the lab and you were a perfect human being, which most of you guys are really close, but if all conditions were perfect, there were no human error, you would get this perfect yield. Perfect yield, theoretical yield, is usually the larger number that we're dealing with, usually in grams, okay? It can be moles, but usually it's in grams. Because the actual yield is, in reality, what we're going to get. We do make error, we lose product, we make mistakes, we don't get all of the fluid out of a graduated cylinder and so forth. So usually it's the smaller number that we are dealing with. So most of the time when people get percent yield, a really, really good student might get what percent yield? 98, right? A really good student might get like, I'm going to say 90% and up yield. That means that you did a fantastic job. Your actual yield was very, very close to the theoretical yield. A really poor yield might be what? 70 or lower, like 5% yield, right? In the lab I was working with in the summer, people were getting like 30% yield, and they're like, what? Yeah. They were like partying because it's really hard to get fantastic yield, sometimes through some of the experiments you do. So actual yield over theoretical yield times 100 is going to be how we get percent yield. How is percent yield different than percent error? What is percent error? The formula.
Accepted value
Accepted.
over minus achieved value.
I'm going to say experimental. Cool. Okay. Over accepted. Right. Absolute value times 100. So error, what's a good error? Percent error.
0.
Okay, really is 0, but I'm going to go 5% error is good. 100% error, you have done something wrong, right? We've all had that problem. So you want low percent error, but you want high percent yield. Those are two different things. Please make sure you commit that to memory. All right, so what is going to tell us our theoretical yield? It's going to be the reactants that we have. Those reactants, one of them is going to be usually limiting us, one of them is going to be left over in excess. The limiting one will produce the smallest amount of product. So would you want to use the most expensive reactant or the least expensive reactant as your limiting? Because you don't want to waste it, right? If you use your most expensive as the excess, it's just there and it's contaminated and it's excess, you have to throw it away. So usually you'll use your most expensive one as your limiting so you don't waste anything. And so in my class we did this little peanut butter jelly thing, but I'm not going to do that right now. So it limits the extent of the reaction. I'm going to go from here because if you want this later, you have access. All right, so I'm going to talk through this one first, and then we'll go into like a new way we have to figure out how to do this. So tell me, when you're reading this problem, you see the word excess hydrogen. Automatically, what do you know?
That's your excess?
That's your excess, and what else?
Nitrogen, humidity.
Okay, so nitrogen is your limiting. So you don't have to figure out who your LR is because you already know. So whenever you read a problem like this, you automatically know which one is your limiting. And if you were to do this, and we'll just kind of, you don't have to write, you can if you want to, you would say, okay, tell me what each of these things are that are in the problem, like the identities of them. So next experiment, a student collects 8.7 grams of ammonia. Okay, that is the product, so you know the product is ammonia. What do you know, what is this? Actual yield, because it says a student collects. And if they're talking about this is AY, actual yield. If a student's collecting something, they are actually in the lab doing it. You're not going to get in the middle of the class and do it, but it's on the paper, right? From the reaction of 9 grams of nitrogen, what is that? Okay, so one given, 9 grams. And nitrogen, how do we write that? In 2, good. In a reaction, you have diatomics because we are dealing with the full molecular structure, so it's the molecule of nitrogen, not the atom of nitrogen. So we have nitrogen plus hydrogen yielding ammonia. Balance that? Okay, cool. I think it's good, right? 2, 6, okay. So you're starting with this, and you already know your LR, so from here, can you get to, well, actually tell me, what do you need to get to answer the question of what is the percent yield? Theoretical yield. So you're getting to, really, your question's not percent yield yet. Your first question is what's theoretical yield? And who's controlling theoretical yield? Nitrogen, because nitrogen is your limiting reagent, whereas hydrogen is your excess reagent. So in this case, we already know, so we take grams of nitrogen to what? Like at the very, very end. Your real question is getting 2 grams of ammonia that it can make. So you're going to take grams of nitrogen to what? I'm not going to write this down. To moles of nitrogen to moles of ammonia, and then moles of ammonia to grams of ammonia. So once you get your theoretical yield of 10.9 grams of ammonia, then this is your theoretical yield. Okay, that's your theoretical yield. That is your actual yield. Does it make sense so far, like logically? Yeah, the person's not perfect. They have lesser of the actual yield. There's a theoretical yield that's greater. So then how do you get percent yield? So 8.70 grams of ammonia over 10.9 grams of ammonia. And yeah, 10.9 is what I got. Okay. Times 100, and that is 79.8. Oh, 79.8%. So not bad. Pretty good. Okay, so the only thing I wanted to really make note of on this one is if you solve, like some people like to round to sig figs every single step, do not round on sig figs until your very, very final answer because it's called double or triple rounding. So here you saw that you only need 2 sig figs in the problem, right? Or in the final answer. when you get to your, finally through all your stoichiometry, you get to your grams of ammonia. I recorded 3. If your calculator has more, take that. It could have 50. It's cool. That's not a final answer. This is going to be our final. So is this correct? No. So you need to have that to correct sig figs of 2. But if you take this and you round it now, I think either way you would have had, no, actually I rounded it, double rounded and then single rounded. If you double round, you round down to 79. If you single round the correct way, this rounds up to 80%. But 80 points because you need 2 sig figs. So, and we'll go over sig figs every day. Okay, so this is the big one, okay? And then I'll let you guys do. This one's an easier one. Number 5 is a little harder, and I'll walk you through both if I need to. Tell me how you would like to start this problem, and then I'm going to tell you how to do this BDA table before, during, and after reaction. Tell me your thoughts. What are you thinking? Nothing, anything.
How many grams of zinc sulfide?
Okay, so your question is grams of zinc sulfide. Thank you. It's another first step. Set the reaction, right? So what's our reaction? Okay, and write this big on the top of your, kind of like towards the top of your paper. If you need more space, get another sheet of paper out. And we're going to make a table underneath it, just to model what you should be doing, and then you can fill out the table as needed. So zinc plus sulfur diatomic. No, what are the diatomics again?
Carbon, nitrogen, oxygen.
Not carbon, lies, not carbon. It's the big 7. Right?
Nitrogen, oxygen, fluorine, bromine, and iodine.
Chlorine. Oh, sorry, fluorine's supposed to be on the 7. Fluorine, chlorine, bromine, iodide, and hydrogen. Okay, it's the big 7 and hydrogen are the diatomics. Are there 7 there? Yes, 7. 7 diatomics. Okay, sulfur is not one of them. All right, so that forms zinc sulfide. Guess what? It's a 1-to-1-to-1 ratio. Fantastic. Okay, so what I'd like for you to do is start trying to get used to this before reaction, during reaction, and after reaction table. Because sometimes you will literally have to calculate 4 things from one problem, and the table does all of it for you if you keep it organized. So what I do is I write underneath each of the columns the designated givens. So I have 25 grams of zinc, 25.0 grams of zinc. I have 30.0 grams of sulfur. From here, I have no idea who the LR is. The LR is based on the mole-to-mole recipe, not the gram-to-gram recipe, because one of them will run out first, okay? So I need to first convert both of these to moles. I don't even ask for you to show me that conversion half the time, because it's molar mass people. You're just dividing by zincs, which is like, I forgot. What zincs?
65.
Thank you. I was going to say 50 something. Okay, so this one is divided by 65.38 grams of zinc because that's its molar mass. So it's technically you're doing like times 1 mole over 65.38, but I'm just dividing it here. So to convert this to moles, you do times 1 mole over 32? Yeah, 32.96 grams of sulfur. So here we're going to have moles of each. So when you finally do that, I got you on calculations. It's 0.382 moles of zinc and 0.936 moles of sulfur. And if you need to draw like a little line between your stuff to keep them separated, that's fine. So all we've done so far is what? No. What have we done so far? All we've done is convert to moles, right? Isn't that basically the first step in every problem? Basically, okay? So here is the part where you get to do a trick in your head. Before in honors chemistry, and you don't write this down because I try not to make you guys do this here. Before in honors chemistry, what you've done is you go, okay, I've got 0.382 moles of zinc. That's how much I have. And then you have to figure out what you needed of the other. So you had this much. It reacts in a 1-to-1 mole ratio. So how much do you need of sulfur to fully react with all that zinc? The same thing, right? Do you have enough sulfur to react?
Yes.
Totally. Look at all that. You got like 0.9 there. You only need 0.3. So right now, who's your LR? Zinc, because you have a surplus. You have an excess of sulfur. So you can do that in your head sometimes. But there's another way markers. There's another way of doing it. I want you to write this part down. So we just decided that this 1-to-1 ratio is super easy to work with. So we already know this part. This is your LR, this is your excess. But the way I'd like for you to do it in the future is in your head, say, take your moles of your zinc, divide it by its coefficient of 1. Okay, it's 0.3, blah, blah, blah. Take this one, divide it by its own coefficient of 1, it's 0.9, which is less zinc. Zinc runs out first. So the rule is divide by your own coefficient, and if you are lesser, you run out first. You are the LR. Because whenever you're dividing by your own coefficient, you're breaking them down to the ratio in which they react, and whoever has less is going to then be the LR and run out. So you can try to have any method in your head that way, or you can do the whole divide by your own coefficient and who's less. Again, zinc is our LR, sulfur is our excess. So, do I really care about sulfur at this point? Not really. It's not controlling anything. It's just zinc. Zinc is the main guy you want to be looking at. So during this reaction, before this reaction begins, you have this much zinc and this much sulfur. Do you have any zinc sulfide? No, the reaction hasn't even started, right? You have 0 there. During this reaction, all of this goes away. So you subtract 0.382 moles here. You do subtract some here, and I'm going to write it here just for completing the table's sake. You subtract 0.3 moles here. What ratio, though, does this react in? A 1-to-1. So you're subtracting the amount of the LR from the two reactants and the ratio that it reacts. So this one over this one. So you always put, if you make that start here, put coefficient of your LR on the denominator. This one you can't tell because they're both ones. Okay, bye. Okay, so then over here, you're adding LR's amount, 0.382 moles, and a ratio of 1 over coefficient of LR 1. It's different, of course, if you have a bigger, badder problem. This one's easy. So, the very end of the reaction, and I know this question you don't have to do the whole table for. The very end of the problem, you're basically trying to figure out how much zinc sulfide should be able to be produced. So 0 plus this, easy again, 0.382 moles of zinc sulfide is produced. How much of your LR is left? 0. And some number of moles, what is this? 0.584, thank you. Moles of sulfur is remaining. So a bigger problem, I would say, how much is produced, what's left over, what percent of reactants are reacted. Like, I could ask you a lot more on this, and the table completes it for you. It gives you a lot of information. And then you would take this 2 grams to make your final call. 1 mole of zinc sulfide is 97.44 grams. So, on all, and here it is, how many grams of excess reagent should be remaining? To take the moles to grams there. The point is, I would like for you to start getting to the before, during, and after reaction, because we're going to use them a lot more in Unit 2. And then we'll go into a version of this with acid-base reactions and equilibrium. So it's going to kind of continue with this. The sooner you start, the better. So you guys tell me, you want to start number 5? Oops, I'll come back to that. You guys want to start number 5? Ask a buddy and ask me, and I will do it for you if you want me to. Okay? It's 8:30. We still have 38 minutes. Yay. So try this one, and I want to make sure you're with it and do your other stuff. I did not record that at all here. I'll scroll up and kind of just save this. I forgot to record on that one. Most of your stuff isn't in order unless you like dropped your folder. This is your more reaction stoichiometry, so 86, 87, 89 are the 3 problems I want you guys to do. And you can save those from home. You should be okay with that. This is that optional textbook homework. I will not do a student presenter tomorrow. Who was that going to be? That was going to be Jake, but don't worry about that, okay? Though I'm going to try to stick with the recipes. I'm supposed to present that whenever that is, and I'm going to try to stick with my dates of homework. If you guys want this, I already posted this online too. I think I did. But if you want to take a picture, know when you're presenting a homework problem. That's it. So nobody's presenting tomorrow. No worries. A couple of people, Jack, Straw, and Lewis, you're presenting on unit review day, which is the very end. Summer problems will present on unit review day as well. Shannon and Maggie. I can't remember what this is. Diamond. It's probably empirical formula, which will be in like 2 days. Combustion practice will be in a couple of days. Chelsea, Josh, I don't remember. I'll have to look. Okay, but I will post this online. No worries. Oh, squirrel. Sorry, random thought. You have a problem on the summer assignment that you cannot do. It's ionic molarity. It's number 7. Omit that on your summer assignment if you couldn't do it anyway. Okay. 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 So this is your solution density lab. Okay. I want you to probably get your pre-lab assignment done in class. You can ask me questions, but specifically make a star on these couple of pieces that I've highlighted, okay? So what I need you to be aware of is extensive versus intensive properties. So mass and volume are extensive properties, meaning that it depends upon the amount present. So like intrinsic motivation versus extrinsic motivation. Who is extrinsically motivated by money and candy and chocolate? You and me. I mean, I like getting chocolate and cake too, yeah. But intrinsic motivation means that you have a personal goal kind of thing, right? So it's internal. Anyway, mass and volume are extrinsic, and density, which is a ratio of them, is actually independent or is intrinsic because it cancels each other out basically on their extrinsic properties. We all know what density is though. This is the part that everybody misses in the lab. So I'm trying to point out misconceptions before you even have the misconception, so we don't have to deal with it. Whenever you get on this lab, you're going to notice you're dealing with Epsom salt, which is magnesium sulfate heptahydrate. Magnesium sulfate heptahydrate. Okay? And part of it is water, but it's not 100% water, nor is it 100% magnesium sulfate. Okay? So what you're going to max out at is whenever you're doing this, you can have minimum, whenever you're putting these ratios together in the hydrate form, minimum, if it's just water and 0% magnesium sulfate, obviously it's 100% water, there's nothing in it, there's no solute. The density of water is 1 gram per milliliter. If you didn't know that, you should. And then you can get up at this compound, you can get up to 26% magnesium sulfate and 74% water based on their masses. Okay, so if in a problem you're calculating something and you get like Epsom salt is 50% water, 50% magnesium sulfate, you've done something wrong, because that is the absolute maximum at room temperature, at saturation point, when all the Epsom salt is dissolved into a solution. So just be aware of that, and you can reflect on your answers because you know that's the max it should be. Okay, that's how you know if you're right or not. I'm trying to give you that hint up front. Other than that, you guys should be able to do these just fine. Yesterday we had some people lined up at the scales. If you feel like you want to come in at lunch or after school, you can mass out all your magnesium sulfate. It'll take you 5 or 10 minutes, and you can start dissolving them if you want to. I will tell you they do take a while to dissolve if you want to do any of that today. Okay, so you guys go to your labs, divide and conquer. Look at pre-labs those specifically. Oh, do this on a separate sheet of paper. Leave your lab notebooks at your desk because I need to just check for completion right now. Sorry, I'm going to say that very painful talk. So do that like on a separate sheet of paper. You can take it in your lab notebook later and do anything else in your lab notebook. Leave your lab notebook on your desk, and I will come for it. Thank you.